Hi everyone, welcome to the second session of Introduction to Research. My name is Rashmi. I'm one of the people who are going to be on the class today. I don't know what to call this. Tara?
Actually, Mo, yeah.
Okay. Well, I was going to say that we hope that all of you have had a chance to revise the material in Chapter 1 and also to go through the material in Chapter 2 and think of the kinds of questions that you want to ask. I also hope that you have had a chance to look at our responses to the questions, the written responses. And we would encourage you to keep asking questions both through the chat box and through email. Especially email, use that opportunity to ask questions. Is that?
Okay, so hello everyone. Last week we had said that you would be meeting more of the ThinQ members as we go along. So today we have Rashmi. Rashmi has already introduced herself. We also have Saili. Hi Saili, you want to say hi?
Hello.
And we had Yadu and joining Aditi behind the scenes. Okay, we'll probably get to see him sometime. Now, as Mo said, we hope you've read Chapter 2 and have come prepared to, engage with the session.
Yeah.
One of the ways we had said you could ask questions was by sending us email beforehand with your questions before this live session so that we could pick up those questions during the session. And also that we would give priority to those questions. Now, we've had 2 questions. So shall we just, before we go into today's session, shall we just go into the, go to the questions? One question was, I'll read it out, where and how do we find reliable sources for collecting data? This was a fun question for us because we learned something from it in the sense that we thought we understood the question and then talked about it and realized that there were other possible ways of interpreting it. And it was like throwing this back at us that we have to make sure that we clarify every word in a question when we're dealing with it. So this is something that's going to be throughout, something that's going to happen throughout your research. The need to clarify questions. And actually, in the next session, that's what we will go into.
In Chapter 3.
Yeah. So this question, where and how do we find reliable sources for collecting data? Do you want to address that?
Yeah. Actually, I have a confession to make. Initially, when I read that question, I thought, how can I answer that question? I interpreted the word reliable to mean dependable, something that is useful, etc., in a general sense of the word. And I said, this is like asking, how do I learn to choreograph a dance in ballet? Or how do I learn to write poetry? It's too big a question. The only way to address that question is to take somebody through the entire course. It's not something that can be answered in a few sentences. And then when we were talking about it at the dining table, it occurred to us that maybe the question was about reliability of sampling, which is a very technical notion. That's if you have a sample and if you take a sub-sample from the, 2 different sub-samples from a sample, do they give you the same conclusion? That's a question that reliability is asking. That part is a procedural, technical thing that can be answered fairly easily. So then it occurred to us that people could be asking us about procedures. And procedures are easily learnable, with some practice, you can learn how to execute those procedures. But then there are the other aspects of research, like the strategies or the art and craft of research and so on, which will take a long time. So we have to separate them. So our mistake was that we interpreted initially the question as a general question in ordinary sense of reliable. And then it occurred to us that is not what it means. It means reliability as a notion, statistical sampling.
I hope we got it right this time.
Okay.
The second question, it had to do with methodology. You want to?
Yes. Actually, there were one question about methodology, because if you look at the use of the word methodology in normal research, introduction to research courses or introduction to research methodology, I actually did a sampling today. I did a Google search, no, actually YouTube search for introduction to research methodology or introduction to research.
Can I interrupt for a moment?
Yeah.
This was not really a question. It was more like telling us that what we have said about methodology in the chapter is not quite what others understand by methodology.
Yeah.
And so it was confusing. And that's why we are addressing it. Yeah.
In most courses, not just most courses, all the courses that I've seen on YouTube, methodology means ways of gathering data. So they talk about, for example, focus group, they talk about interviews, they talk about surveys, they talk about quantitative methods, qualitative methods, they talk about case studies, fieldwork, and a whole bunch of things. Instruments, experiments, all these are different ways of gathering data and then processing it and so on. The way we are using the word methodology, it's very distinct from these courses. Methodology is ways of looking for answers. That means the word methodology applies to mathematics, for example, research in mathematics, which you don't use data for that kind of research. Also in philosophy, you don't use data, but methodology applies to those. Literary criticism. Also in theoretical research, we use the observational generalizations that experimentalists have come out with. So these things do not come under methodology in the standard courses. But our focus will be on these aspects of methodology, which includes things like how do you justify something? How do you prove that something is true? How do you choose between alternatives? These are not usually discussed under the word methodology in most research courses. So this is very different. So keep the two meanings very different. Right?
All right.
Okay.
Okay. Shall you want to now proceed then to the process of research, which for us is there in the diagram that you have in both chapters.
Yeah.
And methodology as being one component of it.
Yeah.
I want to talk about that and the expansion of
that. Yeah,
that's
true. We did that
notion.
In chapter 2.
Yes.
So in chapter 1, we talked about 4 components of research. One was research question. Of course, before you get to the research question, there is some degree of reflection, accidents, and autobiography that happens. But we are going to begin with research question or research problem, followed by looking for ways of answering the question. That is what we call methodology. And then we find the answer. And on the basis of the answer, you will think again and arrive at a conclusion on the basis of the answer. So these are the 4 components of research that we presented in chapter 1. But in chapter 2, we expanded on that notion. And there were 2 important things that we added in chapter 2.
One was critical thinking.
Critical thinking.
Right.
So critical thinking applies to all these components. And the other part was
justification.
Justification. When we come up with a conclusion, it is important to justify the conclusion to the satisfaction of the research community. And we also pointed out that the question that we start out with may not be the question that we end with, because after we have gathered some data, thought about it, we may come back and revise that question. We're going to see examples of that today. In fact, you saw examples of that in chapter 2, when the question kept being refined and revised. So these are some of the things that we would like to point out in chapter 2.
Yeah, and one other thing that came up in chapter 2 was that when you talk about research questions, so in the picture that you have on the screen right now, we've called it a question. But a lot of people find that kind of uncomfortable and would prefer to call it a problem. So it's either a question to be answered or a problem to be solved. And we said in the chapter that this was just, each one could be formulated as the other, and that they were just 2 different ways of looking at something. So it's there in the chapter, so we won't elaborate.
So to give a simple example, the question, how do you cure cancer? Is that a question? Yes. Is that a problem? Yes, the problem of cancer is a problem. So these are slightly different ways of looking at the same starting point.
So perhaps this just occurred to me, it's not there in the chapter.
Yeah.
We could think of it as the question typically as being a research question. You start exploring and looking for an answer. And then once you have an answer, see how you implement it. And, that problem typically involves the implementation.
Yeah.
That could be one reason why people are uncomfortable with just calling it a question.
But there is also, mathematicians quite often talk about research problems.
Right. Okay.
Right? Even if there is no application.
Yeah.
There's simply terminological difference.
Yeah. A difference in perspective.
Yeah.
Okay. So I think with that, we should plunge into methodological strategies. Yeah.
So to give you a sense of methodological strategies, we used 3 examples. Our first example, what was the first example?
The first example, the question was, it had to do with, do exams improve, do curricula improve thinking abilities? And we refined that question until we got to a point where we said, do examinations test the thinking abilities needed for research?
So the reason why we revised the question was, first of all, when you phrase it in terms of curricula and thinking abilities, we have to define curricula, we have to define thinking abilities, and it included way too many things. And this was not something that could be done in a research project, let's say, of a year or 2 or 3 years. It was too huge. So we narrowed it down to, instead of curricula, we took one piece of the curriculum, namely the assessment. And instead of thinking abilities as a whole, all kinds of thinking abilities, we said thinking abilities needed for research. And these are reasonably narrow concepts, and this is doable. This is something that we can do in a year or 2. So this happens quite often. The research question keeps revising.
This is actually not often. It happens most of the time, because you start out, you don't know what you're looking for exactly. You have a general area, and then as you proceed, you find the need to narrow or sometimes broaden your question. And what you saw here was an example of narrowing it in such a way that it was actually a feasible kind of project.
I also want to point out that we looked at the meanings of the words in the question. Before we can answer a question, we should know what the question is. So this was an example of that. And we're going to talk about it in the next chapter, the conceptual clarification of the terms in the question. So that covered the first example.
Right. The second one had to do with biological evolution.
Yes. So our question, if I remember, was, is Darwin's theory of biological evolution true? So when you ask the question, is it true, it might be useful to summarize it in one sentence. Say, what exactly is the central claim that Darwin makes? That is not an easy question to answer. So we discussed that issue first. What is the question? And we said there are many ways of thinking about Darwin's central claim, not subsidiary claims. And one way of formulating that central claim is the following.
Actually, I'll just read it out.
Okay.
So the claim is, all the existing and extinct species on Earth evolved from a single ancestor species or a small number of ancestor species.
Yes. The second part is actually interesting, because Darwin did not specify a single ancestor species. He left it open. But quite often in textbooks, we see it stated as single ancestor species. This is not what Darwin actually said in The Origin of the Species. But there is still a problem, namely, what does it mean to say species? Okay, if you formulate the research claim in terms of species, you have to define species. And that is not trivial. In fact, Darwin knew it was very difficult to define. And even today, there are so many definitions of species. But until we are clear about what we mean by species, that is not a question that can be answered. So this was one of the points made in that discussion.
And once you've clarified all of that, The next thing is to ask, how do you go about this? What are the questions you need to ask?
Yeah.
One is, what are the kinds of phenomena, observable phenomena, that would come under the scope of the theory? Right?
Yeah.
And then you ask, how does the theory explain this? How does it seek to explain it? How does it try to explain it? And once you've succeeded in explaining something, you ask, is the theory successful in explaining it?
Yeah. So to give you a brief pointer, one of the things that Darwin tries to explain is what is called homology. By homology, we mean anatomical structures or functions that are similar across species. So if you look at the hand of a human being, there are 3 pieces in the hand. And you see exactly the same pattern on all mammals, on birds, and so on. So this is what biologists call homology. So how come different species have the same pattern? That's one of the questions asked. And Darwin's answer was that they have the same pattern because of evolution, and he defines it in terms of descent with modification. You have ancestry, and then there are some differences made, but then certain aspects remain constant in the course of evolution. The other thing that evolutionary theory tries to explain is fossil evidence. We are not going to go into some of those details, but we need to have some understanding of what the scope is so that we can ask the question, what kind of evidence, if it did exist, will show the theory is wrong? This is extremely important in science. So what are the things that the theory predicts, and what kinds of things, if the evidence, if they existed, would show that the theory is false?
Or would support the theory.
Support the theory too, yes. Yeah.
Okay, you want to go to the third example, or is there something else that...
No, what's the third example?
The third example is straight angle triangles. So,
oh, yes, okay.
So we started out with observational inquiry within science. Then the next question had to do with theoretical research. And now we move on to mathematics.
To mathematics, where you don't need data. In fact, you don't use data to show that a theorem is true in mathematics. This is crucial. So methodology in mathematics would be of that kind, methodology that doesn't use data, as we mentioned earlier. So this is an interesting question, because whether or not straight angle triangles exist depends upon how you define the term triangle. This was what we tried to do in our example. So if you define triangle as in terms of 3 vertices which are non-collinear, what that means is that 3 vertices should not be in a single straight line. If that is part of the definition, the answer to the question is no, straight angle triangles cannot exist. You can go through the discussion to find out how this is proved. On the other hand, if you define triangle as simply in terms of 3 vertices and 3 straight lines connecting them, then it is possible to have triangles which have straight angles. And what that means is that the other 2 angles will be 0. So it would look like a straight line with 3 points, but that is a triangle. Even though it may not look like a triangle, that is possible. So this is an interesting idea, because what it shows is that in mathematics, or also, of course, in other places as well, the truth of a claim depends upon the definition in the claim. This is a somewhat surprising result for most people. So do pay attention. We are going to come across this kind of situation again and again in academic research.
Yes, so an object with 3 lines and 3 vertices, but looking like a straight line, has actually been called a degenerate triangle.
Yes. Yeah.
So,
this is the terminology that mathematicians use. Yeah.
So those are the 3 examples.
Yeah.
Before we go on, any quick clarificatory questions, very quickly?
Has somebody typed questions in the chat box that we should answer?
If not, we'll carry on.
Rashmi, Saili.
All right.
Yeah, there's no specific questions. I think they are questions that would need some time to engage with, so we could do them in the end.
Okay. We'll pick them up at the end.
Okay.
Yes. Okay, so we'll move on then.
Yeah. So what was the next after the examples? Actually, after the examples, we simply wrapped up, right, in the chapter.
I think we could wrap up, because we're assuming that the chapter itself was the examples were fairly detailed, discussed in detail, and so we could just go on to wrap up then. Yeah.
And in these videos, the sessions, we are not going to summarize everything that we have written in the chapters. We expect you to have read the chapters, maybe once or twice or even 3 times, discuss them with your friends in affinity groups. And if there are things that you don't understand, we expect you to write to us through email about your problems. So there's a lot of homework to be done before you come to the live sessions.
Yeah. Okay, but there are a couple of points I think that might be useful to highlight.
Okay.
Right?
Yeah. You want to do that?
Sure. So in chapter 1, we started out with with the process of research, and then expanded it in a picture in chapter 2. And well, I think I don't need to go into details of that. But we had these 3 examples, and one of the takeaways from that should be that they were from 3 different domains: observational research and science, theoretical science, and mathematics. And what you saw was differences across these domains in the methodologies that are used to look for an answer. However, they have certain fundamental attributes that all of them share. And I think, so in spite of the differences, what we need to keep an eye out for is the similarities. Now, we won't go into the details here, but as we go along and we see more examples, you'll see what it is that is shared across domains.
Yeah.
And those would then be our transdisciplinary strategies of research. Another thing that came out again, as it did in the first session, was the importance of looking at the words in a question, in a research question, or in anything at all, and clarifying the meanings of those words, being very clear about what they mean. Otherwise, what happened to us with one of your questions about reliability, that can happen to any of us. Yes.
And in fact, that's an example of what different forms of research have in common. This conceptual clarification is essential whether you're doing mathematics or philosophy or history or physics, doesn't matter.
And it's so central to research that I think the next chapter in the next session are devoted to that.
Yeah.
So we'll get back.
We'll be talking about many other things, like reasoning, for example, is central to all of them. So look at what is common to all of them, and at the same time, keep an eye on the differences. Both. You have to juggle with these 2 aspects. The whole course is going to be like that.
Yes. Yeah. Anything else that, before we go to questions, anything to highlight?
As far as I'm concerned, no. How about you?
Right.
Yeah. Okay. So that's our summary of chapter 2. Now it's up to you to ask questions.
Okay. So we have a question from the Discord forum. And it is a question from the affinity group, Linguistics, Learning and Sharing. So the question is that from the chapter 2, we learned that critical thinking is a very crucial component in doing research. May we know more about this ability and how to develop critical thinking?
Well, we're going to devote about 2 chapters towards the end of this course. But initially, a very brief idea would be critical thinking is the in the case of research, not the other kinds of critical thinking, will be the examination of the considerations relevant to a claim and making a decision on whether to accept the claim or not. That's critical thinking. So what that means is that you look at possible reasons for accepting the claim and possible reasons for not accepting the claim. And we actually gave an example of critical thinking in the question, should we believe that the evolutionary theory proposed by Darwin is true? That's a question about critical thinking. Usually what happens is when you see something in a textbook, you simply accept it. And we are suggesting that we shouldn't do that. We should ask ourselves, should we believe what the textbook says? Should we accept it? Or should we reject it? Or should we accept it partly? That is where critical thinking begins. A critical stance is a skeptical stance. It says, I'm not going to accept everything that people tell me. I'm going to make that decision on my own. So one of the advantages of learning how to do research is that this ability to make those decisions on your own without having to depend upon other people, that ability develops. And you will see this all over the place. So somebody defines, for example, liquid as something that has fixed volume but takes the shape of a container. We have mentioned this in one of the examples. Instead of accepting it blindly, you should ask, does this definition of liquid work? The moment you ask that question, you discover that the definition doesn't work. You have to reject it. There are many such things that you're going to find in your textbooks, in research articles, in the media, all over the place.
Actually, critical thinking is not restricted to academia or to research. So, for example, imagine a child. Somebody tells a child, you shouldn't, what you're doing is telling a lie, you shouldn't tell lies. And the child turns around and says, but you told a lie in such and such situation, so why shouldn't I? That the child is thinking critically, because it's looking at contradictions, looking at examples that go against what is being said, and so on. So it begins there. Now, what you need to do is bring the questioning, doubting, and questioning into whatever you encounter. That's what you're doing in research.
There's a funny example. There's a little child, 5-year-old, saying, when I grow older, I want to marry my grandmother. And the father says, you can't do that. That's my mother. You cannot marry my mother. And the child says, but you married my mother. Why can't I marry your mother? It's a funny example, but the child's spirit is really that about critical thinking. Yeah.
I just wanted to add something to that. So, we were talking about how you shouldn't accept a conclusion just because somebody has told you to. But if supposing you think critically and accept or reject the conclusion, you should also be critical of yourself accepting, like your acceptance status. So if you believe in something, that is falsifiable or defeasible too. It's not. That's also part of critical thinking, where you don't, like, just because you have believed something doesn't make it true. So being skeptical of yourself is another component of critical thinking.
Okay. In fact, nice example is this question that we discussed at the beginning about reliability. Our first reaction was, oh, that is not an answerable question. But when we thought about it, we discovered, oh, there is a different interpretation of reliable where it is easily answerable. So all of us make these mistakes.
And critical thinking is not it's not a procedure. It's a process that should happen automatically all the time. And for that, it becomes a part of your habit and part of the way you look at everything, your mindset. Right? So
the first prerequisite is not having total certainty of knowledge. The moment you have total certainty, critical thinking disappears. You have to leave space for a little bit of uncertainty and a sense of fallibility, without which critical thinking cannot exist.
Just to remember that we are all human, and as humans, all of us are capable of making mistakes.
Yeah. Okay, the next question is from Chitra. She asks, how do we choose between different plausible but contradictory theories or explanations to the same phenomenon?
So this is about scientific theory.
Yes.
Right. We're going to discuss some of these things in later chapters. But let us see. Take something that you probably may know about. There are different theories of light, actually. A child thinks of light as a substance that fills the room. If you turn on the electric switch, there is some substance that fills the room, and that allows me to see things. This is typically a child's concept of light. When the child goes to primary school, the child is told that light is not a substance. Well, they don't say that light is not a substance, but they say light is a ray. It's like a straight line with an arrow. And that allows you to explain a large number of things. So it explains things like the pinhole camera and various things. I'm not going to go into the details. And then little later, the child is told that light is a wave. Now, this is actually a very confusing thing. From the idea that light is a substance, the child is told it's a straight line with an arrow. And then the child is told that it's like this. Okay? So does that mean that we have to reject the idea that light is a ray? That's the first thing. And then the child is told that light is a particle. So not like this, but like this. It's like a billiard ball, infinitely small. So there are actually these different theories. And in the 19th century, there was actually a debate between the wave theory of light and the particle theory of light. There was evidence for the particle theory of light. Should I mention photoelectric effect? Well, I'll mention that, but I'm not going to go into the details. There was evidence to show that the particle theory of light did explain certain things. So we should accept that. On the other hand, the wave theory of light also explains certain other things. For example, what you may have learned, like double-slit experiment, Young's double-slit experiment. So what we have here is the particle theory can explain certain things. The wave theory can explain certain other things, but they are logically contradictory. You can't accept both. You can't accept the fact that light is a particle and light is a wave, which means light is not a particle. So you have to choose between them. In this particular case, the solution to the logical contradiction was, well, it is neither. We won't go into the details, but just an example. What it said was that from certain perspective, it looks like a particle. From other perspective, it looks like a wave. It is neither.
Yeah, and
Right.
Chitra, you will see more examples of this as we go along.
Yeah.
Which will probably help you understand this better.
We are going to discuss this at great length in our discussion of the heliocentric theory and the geocentric theory, which will be in chapter,
one of the
chapters 5, 6, 7,
chapters.
one of those.
Okay, the next question is from Edna. The question is that I didn't clearly get the use of the word finding. Is it just the data gathered relevant, which is relevant to a question, or it is something that you find out from the data that is relevant to the question? So what exactly is finding?
Yeah, finding is used typically in the data type research, that is in scientific research. What the data shows, which everybody would accept. So if you measure the height of men and the height of women, take a large sample, let's say a random sample of 20,000 men and women, and you take the average height of the man and of men and the average height of women, you'll find that the average height of men is more than the average height of women. That's a kind of finding. I don't think anybody would dispute that if the data were gathered, in a responsible fashion. But the question is, now you have to explain why that is so. Okay. Now you move from the finding to other kinds of questions, the explanation for the finding. So finding is roughly what we have called observational generalization.
What you could think of it as the pattern that you find in the data.
Yeah.
I hope that answers the question.
If it's not clear, you have to ask your question again and tell us what it is that you didn't get.
Okay, the next question is from Sobi Maya. Can any scientific theory be verified to be true, or can we only improve the accuracy or disprove a theory?
Scientific theory, specifically scientific theory.
Scientific theory.
Yes. So.
The earlier concept was that you can prove scientific theories the way you prove mathematical theorems. And in the 19th century, there was a lot of discussion about this, and people kind of agreed, beginning with people like, let's say, Hume. Let's not bother about the details, that deductive proof is impossible in scientific theory. And philosopher Popper pointed out that scientific theories cannot be proved using deductive logic, but they can be refuted. So the idea was falsifiability of scientific theories. But that even though it is true that scientific theories cannot be proved deductively using deductive logic, there are ways of arguing for scientific theories using evidence and arguments. We'll discuss some of those things later. So the short answer to your question is, yes, we can provide arguments against a scientific theory and for a scientific theory and put the two together and we can make a decision. But we cannot say scientific theories can be verified to be true. Verified is too strong, because once it is verified to be true, it cannot be false. It is in the nature of scientific theory that they are fallible. That is, once something that we believe to be true on the basis of justification, rational evidence, may turn out to be false.
Actually, I want to read out a quote from Richard Feynman on that will probably answer your question even better. So, quote, "The scientist has a lot of experience with ignorance and doubt and uncertainty, and this experience is of very great importance, I think. When a scientist doesn't know the answer to a problem, he is ignorant. When he has a hunch as to what the result is, he is uncertain. And when he is pretty darn sure of what the result is going to be, he is still in some doubt. And we found it of paramount importance that in order to progress, we must recognize this ignorance and leave room for doubt." So in other words, you are never 100% sure of your scientific theory.
Tara, there is a similar quote from Einstein.
Yes.
You want to read that out?
I don't know
you
where
don't have it here? Okay.
I may not have it. Yeah. As accessible as this.
Yeah. Okay.
The next question is from Gargi, and she says, usually in a PhD, there are at least 3-4 questions or objectives. So can these questions or objectives be a part of a bigger research question, or should we have different, should we have 3 or 4 different questions?
There is typically an overarching question, right, that brings together the 3 or 4 questions.
Yeah.
In my experience, I haven't seen a PhD thesis or
a really good PhD thesis. Of course, you can write PhD thesis with 24 different questions.
Right, but typically it would have at least, you would be able to frame it as an overarching question.
Yeah.
That would include the sub-questions.
And because of that main question, there is also a central claim.
Yes.
You should be able to say, in this thesis, I intend to show that such and such conclusion is true. You could have subsidiary conclusions coming from subsidiary research questions. It's always a good idea to look for a formulation of your single main question. And that main question could come from some more fundamental question, but that's a different issue.
Actually, sort of since we have a little bit of time, a personal note on this, something that we learned from a master artist, craftsman of research, a teacher of ours, who would ask people when they're finished, when they're presenting something, he would say, "Give me the substance of your thesis in 1 sentence. And then once you've articulated that, give it to me in 3 minutes. And then in 5 minutes. And now write it up as 10 pages."
Yeah.
And that it is then that you really understand what it is that you're asking and what it is that you're looking for, what you're doing.
Yeah.
So.
And if you've written your PhD thesis and this, you have to write that 1 sentence, short sentence, not a sentence that is 10 pages long. it's actually a very harrowing experience.
But it's an extremely useful one.
It took me about 1 week at least to find that one sentence. Right?
Yes.
I don't know how much time it took you, but
a week.
It wasn't easy. But once you do that, that is when you understand what you're trying to say. Until then, you have written your draft, but you don't really understand your own thesis. But that may be a strange thing to say, but both of us have had that experience.
Okay. The next question is from Praveen. He asks how to deconstruct a research question. That is, what aspects to look at within the question that would in fact guide to direct aims or objectives.
I think that's what we meant by conceptual clarification of the words in the question. You ask a question, research question, there'll be 1 word or 2 words or 3 words that are crucial. So in our research question about the first research question that we discussed in chapter 2 about the question about what was that? Was curriculum. Curriculum and thinking. There are 2 crucial words. One is curriculum, and you have to answer the question, what do we mean by the word curriculum? And I'm assuming that when you say deconstruct, what you mean to say is unpack, clarify the concept. So if you have unpacked the concept of curriculum and you have unpacked the concept of thinking, it will tell you how to go about looking for an answer. Or it will also tell you that it is not easy to answer that question, so you may have to change the question in order to do some research on it.
Also, as we said in the first session, there are 2 parts to even coming up with and formulating your research question. There's the art of it and the craft of it, and there's an interplay between them. So, in fact, it's the idea. What is it that you want to look for? That will guide your question, and the question will guide the aims and objectives. So that it's kind of woven together. In inseparable ways. So you have, I mean, if you're asking about a research question that somebody else gives you, or you find somewhere, that's a different story. We're talking about just your question, what you do when you are doing research. You come up with a question, and that has to be something that you want to find out, right? So then once you formulated the question will guide your objectives.
So figuring out exactly what it is that you want to find out, that's not an easy thing to do. But it's important that we agonize over that. And this is not very different from the question, who do I want to get married to? It's not an easy question to answer, right? Research questions are like that.
Okay. The next question is from Chaitanya. So he asks, how important are mathematical proofs in a research paper in the domain of physics?
The physicists normally leave the proofs to mathematicians. And once a mathematician has proved something, the physicists take that theorem and then apply it in physics. Occasionally, though, for a particular problem that a physicist is working in, the mathematicians may not have given the proofs. In such cases, what happens typically is that the physicist doubles up as a mathematician. A clear example is Newton. In order to construct his theory of gravity and motion, Newton needed calculus. Geometry was all worked out by Euclid, so Newton simply borrowed from Euclid. But calculus was something that he needed to construct, so he functioned as a mathematician to create calculus as a theory of mathematics, and then used it in physics. And that kind of stuff happens when a physicist is also a mathematician, or a scientist doesn't have to be a physicist. Scientist is also a mathematician. Chomsky, in order to construct a theory of language, Chomsky constructed a formal system called formal grammar, which is a kind of mathematics. We may need to do that in some cases. When the mathematics doesn't exist, you create this.
Okay. The next question is from Neom. At what point can we be satisfied when defining concepts?
The answer
Never.
is never. Yeah. At some point, you say, "Okay, I don't want to proceed. I'm tired. I can't go any further." And then you say, "I'm stopping. This is it."
And sometimes you say, I think I have a good idea. I think
Yeah.
of what this is. And the next day you find that, no, there's
Yeah.
some counterexample to it. So you're never sure. It's always, tentative, and you need something to go by
Yeah.
to proceed. And you use that tentative, definition to proceed, but you're never sure.
Yeah. So the only answer possible is you stop when you don't have any more energy left. And you say that is it.
Yeah, and when you've used that particular definition for a while, and others see the point of it also, and you don't find any counterexamples and so on, then gradually your conviction of the definition grows, but you're never certain.
Also, there is another thing, that is you have a definition in which there are some words that you should define.
Right.
And you can't keep going on forever, defining every word. So at some point you say, okay, I'm going to assume that everybody knows what it means, which may not be true. But then somebody else will pick up that and they will proceed. So it doesn't matter if you get tired and stop. In research, somebody else will continue your journey.
Yeah, and I think there's more about conceptual clarification in the upcoming chapters. So maybe that will clarify. Yeah. Okay.
Okay. Here's a big question, but I think I'll read part of it. It says, how do you overcome or conquer the analytical or computational gap in research? At some point in research, data screening processing is my bottleneck. I always feel there is something I could do better here to process data. So how do you overcome this bottleneck?
I'm not sure I understand the question.
I don't either.
I think the question seems to be some particular
very
problem that
specialized
you are asking, and I don't know what your problem is, so I don't know how to answer the question. The only way I can think about it is like sometimes you might need a computational system to address your question. And computation is a kind of mathematics. Like when computation is quantitative, you call it calculation. Otherwise, you call it computation. Actually, computation covers both calculation, quantitative and non-quantitative stuff. So you could ask the same question about calculation.
How do you overcome computational gap in this? It's a very, very specific kind of thing.
Perhaps it means something like computational gap means an algorithm does not exist. Is that what is meant? Or the computational system does not exist?
I think whoever asked the question, you might want to clarify the question itself for next time and send it to us. And we'll need time to think about it.
Or just post it on chat right now, and we'll go over it and send you an answer when we can.
Yeah.
Okay. The next question spans several comments, so I'll do my best to read it properly. To how much of an extent can a theory evolve into a completely different theory just by changing the definition of one of its central concepts? This is from Kaustubh. I'll just read the string of comments and then you could respond. For example, Darwin's conceptualization of the species was an arbitrary classification or category of organism created by a competent taxonomist based on morphological characters. Darwin nowhere mentions the concept of the biological species, that is, the definition based on reproductive isolation. However, the modern evolutionary theory, in some sense, depends heavily on the notion of biological species. Does this mean that the modern notion of evolution is a different theory than the one put forward by Darwin? And does it mean that Darwin did not discuss evolution at all by modern standards? Yeah, that's the.
We actually give a kind of answer to that question in chapter 2. If you state the central claim as all the existing species and extinct species evolved from a common ancestor, a small number of ancestors. What that means is that species have been branching, one species yielding two species and so on. And that would explain the existing diversity of life and the homologies. If that is the case, the exact definition of species we can hold. Of course, it is true that we need to define species, and the modern notion of species in terms of reproductive isolation actually doesn't work. We can show you that it's highly problematic. Even today, the coherent notion of species does not exist in biology. We have to look for a theory of species. But what Darwin would say is, I don't know how to define species, but so I'm going to leave that an open question. But no matter how you define species, my claim would stand. And there is another way of thinking about evolutionary theory, which I think if you ask Darwin, he would say yes. Without using the concept of species, you could say, how did such and such variation come to exist in life? So, for example, if you look at the structure of the arm, of human arm, the human leg, birds' legs, birds' wings, skeletal, you have so many similarities and so many differences. The homologies, how do you explain that? And Darwin's answer would be descent with modification. So if you assume that all these variations and all these similarities came to exist through inheritance and modification.
So inheritance gives you the similarity and modification gives you the variation.
Yeah. So this is central to the notion of descent with modification. So the modern theory of biological evolution is simply a refinement of Darwin's theory. We may need to abandon Darwin's theory if you can show that species do not branch off. That is, for example, humans evolved from one species. It could be unicellular. Chimpanzees evolved from a different species, and every species that exists now evolved from a separate species. There is no branchingness. Now, if there is no branchingness in the history of life, then Darwin is wrong.
This is a completely hypothetical example.
Yeah.
You're not saying that that's how it is, but that's the kind of evidence we would need to show that. And to what extent can a theory evolve? Any amount. I mean, I don't think there's any restriction. Depends on what new evidence comes in, new ideas come in, and so on. So.
And the so-called modern synthesis did not actually change Darwinian theory, as I explained just now, in terms of ancestry. Modern synthesis is a theory of the details of the theory of change and the causal causes of change. So it's simply an additional component.
Okay. The next question is from Garvid. He says, is only such research which has applications in our daily life considered as good research? Or is research only used to satisfy, or the kind which is used to satisfy our curiosity, like astrophysics, also good research?
Both.
Yeah.
Usefulness-oriented research is research. Curiosity-driven research is also research.
Understanding-oriented.
Yeah.
We understand better through that. And they're both equally important.
Yeah. And nobody would deny that Einstein's research was serious research. But at the time when Einstein did that stuff, so for example, when he proposed that gravity creates curvature in space, what kind of practical application would you have had if you had asked Einstein at that time? He would have said, my theory has no practical application. However, much later, we discover that it has practical application. Now, the smartphone that you use uses Einstein's theory.
For GPS,
For
example,
GPS systems, you need to use the calculation will be based on gravitational curvature. When Faraday was doing research on electricity,
this is a story.
This is a story. I mean, everybody cites this. Apparently, a British minister came and asked him, Mr. Faraday, all this thing that you call electricity, that's interesting, but what earthly use is it? So he was asking the question, what's a practical application? And the story goes that there are two stories. Faraday said, oh, what use is a newborn babe? That's one. Another answer, we don't really know whether Faraday actually said this, is someday, minister, you're going to tax it. At the time when Faraday was working on the stuff, he could not anticipate the practical applications. Okay. Ramanujan's mentor, Hardy, G.H. Hardy, worked on number theory. And in his book on mathematics, Hardy says, I am proud to be a number theorist because number theory has no practical applications whatsoever.
And yet.
So he was so proud that his theory had no practical applications. But a few years later, they discovered practical applications of cryptology. I'm pretty sure if Hardy had known that, he would have been heartbroken. Because this notion of good research is no practical application.
Okay, I think we have about 3 minutes left.
Yeah, maybe.
So we should.
Yeah. So there's one more. There's one more question from Garvit, which I think is somewhat related. In research, I arrived to a conclusion that there is no answer to the question. Will my research be considered a failure?
This is it's not going to be published, I think, unfortunately, but it will be a contribution. But in the current practical reality of publication, I don't think you will get published. And if you are a young assistant professor looking for a promotion, or if you are a PhD scholar who wants to join the ranks, perhaps don't do that. You do a pilot study, and if you see that you cannot proceed, change your research question.
Also, is it that there is no answer to the question, or is it that you haven't found an answer to the question? Is it something that you can continue doing, looking for an answer for, which sometimes, I mean, finding an answer can take a long time. It depends on that as well.
When the famous physicist Heisenberg was dying, so somebody asked him, so if you meet God, what are you going to ask him? He said, I have two questions for God. I don't know if Heisenberg actually believed in God or not, doesn't matter. And one of the questions that he was concerned with was the nature of turbulence. At his time, physicists could not engage with that question. And they were all troubled that they couldn't answer it. But a few decades later, people discovered a way of modeling turbulence. So sometimes it takes, years. There was a problem at a personal level. There was a question that Tara and I were working on a few decades ago. And we kept working on it. And we found a solution about 7 years later. It took us 7 years. Had we been doing a PhD thesis on that question, that would have been a bad idea. Because you can't, normally, you're not allowed 7 years to do your PhD thesis. But, it could take 7 years, it could take 70 years. Who knows?
Okay, are there any other questions that we haven't answered today?
So there are several more questions, but I think it's time to wrap up now. Maybe we can answer them like later on the document or something like that.
We'll select them. We won't be able to answer all the questions, so we might make a selection.
Yeah. So this may happen all the time, guys. So we're going to have to expect that. Some of the questions may not be answered, and we'll try our best to post answers to that on the forum. Which reminds me, please, add yourself to the discussion forum and ask your questions there. As well as on the email ID. Thank you so much for asking these questions. And I'll hand over to Tara.
Can I just add some things? One is, if possible, send us your question beforehand.
Yeah.
If you have the question as you read. Also, when you ask a question, see if you can do it as part of an affinity group, because that way you discuss it and you clarify each other's, or you answer each other's questions, and then send us the question if you haven't solved it, the problem, or answered it if it's a question. Send it to us as a joint question. And another thing is, we would appreciate it if it's not specific to what you are doing, because we may not have answers to those. And as far as possible, we would like to look at questions that would be useful for everyone.
Yeah.
So just keep that in mind, okay? That this is a collective enterprise.
And to add to what Rashmi said, we have something like 1,600 people registered, out of which only about less than 1,000 are part of the discussion forum. So there's a huge gap. 600 people have not joined the discussion forum. Please join. This is crucial. Okay.
That's it. I think that's all we have.
You're 1 minute late, but that's okay.
That's okay. Yeah. So thanks everyone for the interaction, and thank you for asking all the questions. We'll try our best to get to them in the coming week, and see you next week for the third session.
See you next week.
Bye.
Bye-bye.